I'm Pawan Singh. My contact number is on the screen right now, and today we are going to break down the mechanics of industrial safety. When massive industrial infrastructure fails, our first human instinct is usually to look for a single obvious part to blame. But catastrophic disasters rarely happen in isolation. They are almost always the final result of a long, hidden chain of systemic vulnerabilities. To dissect vulnerabilities, we rely on the logic chain of safety management. First, isolate underlying causes, the magnifying glass, to strengthen defensive barriers. That is the only way to prevent the final accident. Reaching a reality where zero accidents occur is impossible if you rely on reactive guesswork. You have to systematically apply highly structured analytical tools. We start with tools designed specifically to bypass superficial symptoms and locate the true origin of a failure. This diagram illustrates the 5 why analysis, our most direct tool for interrogating a specific problem. By asking why repeatedly and working downward through each reason, investigators isolate the foundational root cause at the bottom of the chain. However, many failures don't follow a single clean line. They often stem from multiple overlapping factors converging at the exact wrong moment. We use the fishbone or Ishikawa diagram to categorize diverse causes. It breaks operations into the 6 M's: man, machine, material, method, environment, and measurement. Isolating variables within each branch maps exactly how they combine to trigger the accident. Identifying that root cause is a crucial first step, but knowing why a component failed doesn't automatically explain how that failure managed to slip past an organization's existing safety protocols. That requires shifting our focus away from the initial error and looking directly at the physical and procedural barriers that were supposed to contain the hazard. The Swiss cheese model illustrates how a multi-layered safety system can let a catastrophic failure slip through. Every barrier has inherent weaknesses, represented by holes. An accident manifests only when systemic weaknesses perfectly align across every layer of defense. The bow tie model visualizes defenses along a timeline. The blue left side maps preventative controls that stop a hazard from triggering the main incident. The orange right side maps reactive mitigation controls that minimize damage after an event occurs. Mapping out defenses this way makes it immediately obvious whether a company has built truly preventative systems or if they are relying almost entirely on damage control. For the most complex industrial environments, investigators have to calculate the exact mathematical and logical pathways of a failure. Fault tree analysis is a top-down deductive tool. Investigators start at a single main event, like a tank explosion, and map backward through logical and OR gates to uncover every combination of basic component failures triggering the disaster. Conversely, event tree analysis is a bottom-up inductive tool mapping future predictive outcomes. It starts on the left with an initiating event, chronologically branching right based entirely on whether subsequent defensive systems succeed or fail. By deploying logic mapping, engineers can transform abstract operational risks into hard calculatable data, allowing them to pinpoint exact failure probabilities across a massive network. What this grid demonstrates is no single analytical tool is robust enough to independently secure a complex industrial operation. Linear interrogation, cause categorization, barrier alignment, and logic mapping serve distinct purposes. They must be deployed together as a tightly interconnected safety ecosystem. When you rigorously understand the underlying causes and effectively fortify your physical barriers, the abstract idea of safety stops being a hopeful goal and becomes an engineered, predictable reality. I'm Pawan Singh, and achieving that zero accident reality is what this toolkit is